Hey everybody. So in one of the last videos, one of the last things we came to was a function like this where we had a corner, and we said that that's a place where a function's not differentiable, right? Where if we took the limit, we saw the limit didn't exist, the limit definition of the derivative, it didn't work. But also intuitively, right, a derivative is helping us find the slope of a tangent line. And the tangent line is this thing that looks a lot like the function, and it's really hard for a line to look like a corner, right? No matter how far you zoom in, you're just always going to have this point abutting to the line. And so it's just really not a good place for us to approximate the function with a line. So there's a couple other ways that this kind of thing or that can be not differentiable that I want to look at. So let's take a look at the following function. F of x is equal to, this will be another piecewise function, x sine of 1 over x if x is not equal to 0. And then we define it to be 0 if the input is 0, okay? Now, this turns out to be continuous. You can take a look at the limit as x approaches 0 and use the squeeze function to see that this is a continuous function. But we now want to see if it's differentiable, in particular, if it's differentiable at 0. Let me rephrase what I said a second ago. This is continuous everywhere because we know that the trig functions are continuous everywhere, as is the function x, and we're multiplying them together. It remains continuous, and we have one problem place at x equals 0 because of that 1 over x. But the way we've plugged it up, it was a removable discontinuity. But is this function differentiable at 0? And let's just take a look at the derivative. So we want to look at f prime of 0. Take the limit as h goes to 0 of f of 0 plus h, so that's just going to be h minus f of 0 all over h. We have the limit as h goes to 0, f of h will be h times sine of 1 over h. F of 0 is 0, so that f of 0 goes away. We've got an h here. The factors of h cancel, and we're left with the sine of 1 over h. So what happens to this? Well, as h is getting closer and closer to 0, I'm gonna neaten that up. As h is getting closer and closer to 0, 1 over h is getting increasingly large, right? If you go from 1 to 1/10, you go from if you take h from 1 to 1/10, getting closer to 0, you're getting 1 over 1 is 1, and then 1 over 1/10 is 10, and then as you go from 1/10 to 1/100th, you pop out up to 100, and then to 1/1000th, you get 1,000, right? We keep that idea of the reciprocal of these tiny numbers is large. But what happens to sine is you keep scrolling through larger and larger numbers. Well, sine does what sine does. It keeps just waving up and down between -1 and 1. And so this limit does not exist because it never hones in on some number. We can make this input here as large as we want by making h as small as we want. And as the input to sine gets larger, the outputs just oscillate between -1 and 1. So this limit does not exist. Okay. And so here's an example of a function that's not differentiable, at least at this point. So at 0, it's not differentiable. Let's get a better intuition as to why, right? That limit might have shown us that it's not differentiable, but maybe it says less about why that's the case. So let's zoom in here. Here's our function, right? So let's look at a few things about it. Notice as we go out towards infinity, the function appears to be approaching 1. This is actually the case. It's related to something we looked at earlier in this video series, the fact that near 0, sine of x over x approaches 1. This is related to that fact, and I'll save that for another time where you can think about how that leads us to this. But we're interested mostly right now in what happens near 0. Well, as we go to 0, as I was discussing before, the 1 over x or 1 over h, 1 over x is just spitting out larger and larger numbers, and sine takes those large numbers and just keeps cycling through its periods, and so we get this function that's waving and waving. And the closer we get to 0, the more frequent that up and down motion becomes. It's always pinned because of that x out front between x and negative x, because sine is always pinned between 1 and -1. So there's the functions x and negative x, and this waving is pinned between them. But as we get closer, it never settles down. And in fact, it only gets worse. The waving only becomes worse. Let's make these lines a little thinner. And we can see, right now the computer's starting to bog down, because there's I mean, in truth, there's an infinite amount of waving happening between any point down here and 0. The computer's rendering as many as it can, but it starts to have trouble, which is why you see these gaps, right? And so, for instance, if we go between 1/1 billionth and 1/1 trillionth, right? This is a really small space between 1/1 billionth and 1/1 trillionth, right? It's less than 1/1 billionth of a unit, which is really tiny, right? In that space of time, you're going to go through what, a trillion minus a billion divided by 6 number of oscillations, roughly, right? It's an immense amount of up and down in this incredibly tiny space, right? Well, what does that have to do with the derivative? Well, if the rate at which we're going up and down is only increasing as we get close to 0, we're never going to pin that line down to any particular tangent line, because as soon as you think you have one, you move just slightly and it goes the other way. It completely reverses direction. And this function just really behaves badly near 0. It doesn't settle down in any way that we can start to make sense out of it. And so it fails to have a derivative there. And it's a pretty cool looking function, I think, as well. Okay, let's talk about another function that fails to be differentiable, also at 0. Let's look at the function g of x. Let's do x to the 1/5. Let's do the same thing. Let's look algebraically and then see what's happening geometrically with a graph. So we're going to take the limit as h goes to 0 of g of 0 plus h, since we're taking the derivative at 0, but that's just going to be h minus g of 0 all over h. So we get the limit as h goes to 0. So g of h will be h to the 1/5. G of 0 is 0. We've got our h in the denominator. The limit as h goes to 0. So the zero we don't have to worry about. H to the 1/5 over h, we're going to have h to the 4/5. Well, what happens to this as h goes towards 0? What happens to this? Well, the 5th root gives us a really tiny, if we're taking really tiny numbers, the 5th root will make them slightly bigger. If they're positive, they'll be positive. If they're negative, the 5th root will be negative as well. But then we take it to the 4th power. So all the negatives become positive. So these are all going to be positives. But more importantly, they're all incredibly tiny. And we're taking the reciprocal. And so this is one of those things, one of the limits that shoots off towards infinity. Right? In other words, this limit doesn't exist, right? We write that it equals infinity to mean it doesn't exist. It just grows without bound. So once again, this limit, the derivative limit, fails to exist, and so this function is not differentiable at 0. Let's jump to the graph. So here's the x to the 5th function, right? This isn't sorry, x to the 1/5. It's the inverse function to x to the 5th, right? And if you remember how the graphs of inverse functions and their inverses relate. They're rotated or reflected over the line y equals x. Let's square this so that they look more like they're a reflection, right? They're reflected over this line. And so what happens if you look at that black graph, that's x to the 5th, imagine its tangent line at 0 is horizontal. Well, its inverse, the one we were just looking at, x to the 5th, when we do that reflection, the tangent line at 0, right, if there is a tangent line, it's this line with a perfectly vertical slope. Right, we've defined the tangent line with this limit definition, and so it's probably slightly improper for me to call it that, but it still satisfies the properties we want. This perfectly vertical line looks just as the closest line to approximating that function there. The problem is the derivative tells us the slope of these lines, and a vertical line doesn't have a slope, right? The rise over the run, there is no run. You're dividing by 0, so there is no slope here. But sometimes we think of that as an infinite slope, right? It's going straight up, which is related to this infinity that popped out of that derivative. So this is these are our examples of a couple other ways that functions can fail to be differentiable. I do also want to mention, I want to look back at that first function that we looked at last time. Let's zoom out to see it. Let's go a little higher. Okay, so now here's this function, this piecewise function. Just because we have a piecewise function doesn't mean it's not differentiable at this point, right? Here we've got a corner. If I take this function and decide, so let's put it this way. Here's the continuation of that line that defines the second half of our piecewise function. If I changed this line, oops, there we go. All right, so I could mess with this, so it's going to keep going through that point. I'm just changing the slope. If I changed it until it matched up with the direction that the parabola it's attached to is moving, now we will have a differentiable function. It turns out that a line with a slope of 6 here, let's show this new function. So now let's get rid of all that. Oops. Right, it looks like, for a second, it looks like the parabola just continues, but what's actually happening is, right, this dotted line is sort of taking over for the parabola at that point. At x equals 3, I guess, is where we switch. And so we can set it up. So just so the fact that we have a piecewise function doesn't mean necessarily that it has to not be differentiable. Let's look at this algebraically. You can see now that it's not a parabola, right? The left half is what a parabola should look like. Here's what the left half of this is made out of, this parabola, x squared minus 1. And so the line that we attach to it keeps going in the direction that the parabola was going at that point where we attached it at x equals 3. The parabola itself keeps bending further upward because as it goes further out, each increase in x gives you a larger increase in y than the one before, whereas with a line, that extra increase doesn't happen. Okay. Let's just go ahead and show that what I claimed was the case algebraically. So the function the original function we had was f of x was equal to x squared minus 1 if x was less than or equal to 3, and it was negative 2x plus 14 if x was greater than 3. We saw before that the derivative at x equals 3 doesn't exist by trying to take that limit definition of the derivative. We looked at the limits from both sides and they weren't the same number. The new function, I named it phi, was x squared minus 1 if x is less than or equal to 3. And then I found that if I made the line that we attached to it 6x minus 10 if x was greater than 3 would make this differentiable at 3. So let's just see that that's the case. Let's compute phi prime of 3. It's going to be the limit as h goes to 0 of phi of 3 plus h minus phi of 3 all over h. However, I now have to take this limit by looking at either side because the definitions of phi change depending on whether h is positive or negative. So let's do some work off to the side up here. Let's look at the limit as h goes to 0 from below of phi of 3 plus h minus phi of 3 all over h. So if we're approaching h 0 from below, h is negative, so we're 3 plus h is something lower than 3. So we look at the first definition, x squared. So we're going to have 3, oops, I forgot my limit. We're going to have the limit as h goes to 0 of 3 plus h squared minus 1 minus phi of 3. Well, phi of 3 is easy enough to do in our heads. X squared minus 1, 3 squared minus 1 is 8 all over h. So here's, oops, this is our limit from below. So again, the limit as h goes to 0 from below, 3 plus h squared is going to give me 9 plus 6h plus h squared minus 1 minus 8 all over h. 9, negative 1, negative 8 goes away. We have 6h plus h squared, but we've got a factor of h in the denominator. So this will become 6 plus h. H goes to 0 and we're left with 6. So the left-hand limit, the limit from the left, from below, is equal to 6. Let's now look at the limit as we approach h 0 from above. The definition looks the same. Except now, if h is positive, we're approaching 0 from above, 3 plus h is greater than 3, so we have to look at this second definition, 6x minus 10. So we have the limit as h goes to 0 from above. We're inputting something bigger than 3, so we use the definition, the second part of this definition, putting in 3 plus h for x, subtract 10. Phi of 3 is again 8, so we'll have minus 8, right? That doesn't change. We get the limit as h goes to 0 from above, so we'll have 18 plus 6h minus 10 minus 8 over h. You can see that the 18 cancels with the minus 10 and the minus 8. Then that factor of h will cancel, and we're left with just 6h, and that limit, with just 6. Factors of h canceled, and the limit of a constant is just a constant. So since the two limits are equal, this limit, the two one-sided limits are equal, then this limit is equal, right? That was our connection between one-sided limits and the limit. And so we see that the function is differentiable there because the slope of the tangent line there would be 6, which happens to be the slope of the line that I connected to the graph at that point, which is how I figured it out. I figured out what I wanted by looking at the one-sided limit of the derivative to see what was happening to that x squared minus 1 there. What tangent line did it look like? What was it doing there? And I just made it continue doing that, right? You can think of it almost like if you were, swinging a rock on a string, right? It's in a circular path, but if all of a sudden the string breaks, it shoots off. Right, if it's traveling around on a string and then the string breaks, it shoots off in whatever direction it was going at the moment it broke. We had a parabola. If you imagine something traveling in a parabolic shape, but then it's whatever's keeping it in that shape breaks, it'll just continue going off straight, whatever it was doing right at the moment it stopped being forced into a parabola. Okay, so let's call that it for this one. We'll do one more to cover a few more ideas about derivatives, a short one. But that's it for this one. Thanks, everybody. See you next time.